Alright guys, we're going to do 5.ds.1 and this is your final presentation in this class. I promised you guys something special, so if you guys answer, I have candy. Alright. So what's given? We're trying to use dynamic scaling to create a model of the Earth's crust. We have all these properties that they gave us, and part A, before we do part A, we need to list the dimensions of each parameter. I'm sure all of you know how to do that from now, and so that's there. So given these, how many dimensionless groups do we expect? So how many parameters do we have? Anyone? Jesse? 7? Catch! Oh, good job. Alright. How many dimensions? Dan? 4. Great. So how many dimensionless groups? Will?
3.
Great. So we have 3 dimensionless groups needed. So that's part A. Awesome. I have lots more. Alright. Okay, so we know how to do this. We want to write the general formula, and we give each of the parameters an exponent. So we have that, and then we want to substitute under each of these. We want to substitute for the dimensions, and then once we have the dimensions, we want to group the similar dimensions to so that the sum of the exponents is 0, so that we can get a dimensionless number. All right. So for m, what's the equation? All right, I said c plus d. But anyway, what's the equation? Just say it. Read it. Catch. Alright, next. Time. Did everyone get that? Awesome. Here you go. Alright, what's the next one? Can you give me length?
A plus B minus 3C plus 2E plus 2F.
Okay, I said temperature. What's temperature?
Minus 3
Alright, right here. And final. Alright, so we have all of our equations. Check to make sure that you have these exponents. So it's pretty simple, pretty straightforward. Make sure that you have the correct signs, because if you notice, some of them are on the denominator, so you want to have a negative sign in front of it. Awesome. So now that we have our equations, we're given our core variables, which are your heat of melting, your heat transfer coefficient, and your speed of moving of the crust. So you set this exponent equal to 1, and then solve your equations by setting the other ones equal to 0, and you get your first pi group. So your first pi group is delta H melt over Cp times the temperature difference. Now that we have this first pi group, can anyone tell me what this means? So we've been working with dimensionless groups, and it might seem like this random group of variables, but what did it actually tell us? Anyone have any guesses? Will?
If you take that data for a certain experiment, all the units will cancel out. You can compare that to numbers.
That's true, but conceptually, what is this number telling us? So what if I added an m in front of the delta H and an m in front of the Cp delta T? Does this ring a bell? M delta H over m Cp delta T? Does that sound like something you guys have done before? So this number is actually a ratio of energies. M delta H is the ratio, it's the energy that it takes to melt the solid. And the denominator, mCp delta T, is the energy that you need to raise the temperature of the solid to its melting point. So what this number gives you is the ratio of those energies. And so that's a physical way by which you can understand what this dimensionless group is telling you. So although it might seem like this random arrangement of parameters, it really isn't. And so if you understand that, you can gain insight from what these dimensionless groups tell us. So similarly, I solved for pi 2 and pi 3. And if you noticed, I removed fractional exponents from my final answer because you don't want to have fractional exponents in your final equation. It's easier to square something than find the square root. And then if you look at this pi group, if you remove this, you see the Cp delta T term on the denominator. And if you group the rest with the K, you get, if you look at the units for just the numerator, you get another energy term. And that's an energy related to the transfer of energy through the crust, divided by, again, the energy it takes for you to raise the temperature of the solid to its melting point. And then finally, for the third dimensionalist group, you have a V squared term. So what if I put an M in front of the V squared? What does that tell you? MV squared, does it sound like something?
Energy.
What energy?
Kinetic
energy. So you get a ratio of the kinetic energy it takes to pull the plates apart over the energy it takes to raise the temperature of the solid to its melting point. So you can gain really good insight from understanding what these dimensionalist groups tell you. Alright, so part C. We needed to use the first pi group to determine the temperature difference for our model. It's pretty simple. You set your dimensionless groups to set them equal to each other. You solve for the variable that you want, that you need, and everything else is given to you. It's literally you plug and shove, and you get that for the model to be dynamically similar, you need a temperature difference of 430 degrees Celsius. That's a lot. Can anyone guess what the melting point of wax is? Guess.
100 degrees.
100 degrees. Anyone else?
80 degrees.
40? Price is right. Whoever comes closest.
50.
Wait,
60. Who says 65? It's 70.
70.
70. So we have the melting point of wax is 70 degrees and absolute zero is negative 273. So theoretical temperature, max temperature difference is what? 343. Great. So that's the maximum temperature difference you could get if you're theoretically at absolute zero. It's a solid. So it's not possible to have a temperature difference of 430 in a model. If you do the same for using pi 2 and pi 3 to determine the wax crust thickness, you find that you would need a thickness of 45 kilometers or a speed of moving the plates of that, which is a ridiculously small number. And then to put those numbers in perspective, that's about half the thickness of the Earth's crust, or 4.5 million Legos stacked on top of each other. And the plate velocity that you would need is about half of that of the Earth's crust. And so, is this model dynamically similar? No. Good work. But anyways, but that's not to say that this model is completely invalid. If you look at the 3 pi groups just for the Earth, you notice that the first pi group is way more important than the other 2 dimensionless groups because the other 2 groups are very, very small in magnitude. And if you compare the first pi group of the Earth to that of wax, you find that they're similar. And so you can gain certain insights from your model just by using these pi groups. So you can use the first pi group to gain information about how the Earth's crust spreads. And so one is way more important than the other 2 pi groups. But yeah, that's the end of the presentation.